Okay, hello everyone. So today's topic is electromagnetic induction. So with this, we start chapter number 6. So in this chapter, we'll be covering electromagnetic induction, Faraday's law, Lenz's law, inductance, AC generator. So these all are very important topics. Okay, so in this lecture, we'll understand the concept of EMI, that is electromagnetic induction, and then we'll solve some questions of Faraday's law. Okay, so let's move forward. Okay, so in this video, we'll see whenever you move a magnet near a coil, so the bulb will glow. So the important thing is, if there is movement of magnet, then only the bulb is glowing, else the bulb is not glowing. Even if you keep the magnet stationary and move the coil, then also this bulb will glow. So what is happening here is, whenever you change magnetic flux through a coil, current will flow in the coil. So to change magnetic flux, either the magnet should come near the coil or magnet should go away from the coil, or the coil should come near to the magnet or the coil should go away from the magnet. So if both are stationary, like you are saying it right now, if both are stationary, then there is no change in magnetic flux because now the flux is constant. Current will only flow if flux changes. So if flux increase, then also there will flow of current. If flux decrease, then also there will be flow of current. But if flux is constant, then there will be no flow of current, like as you can see right now. Okay, so if magnet moves near the coil, then flux will change. If coil moves near the magnet, then also flux will change. Then only current will flow. So for current to flow, flux should change. Okay. So let's take one more example. So in this example, if you'll see, we have two coils. So in one coil, there is a battery. It means current can flow in this coil, and there is a bulb in another coil. So if current will flow, then there will be magnetic field due to this coil, and any coil which has current flowing inside it, it will behave like a magnet. So a current carrying coil is basically has two sides, north pole and south pole, and it behaves like a magnet. So what will happen here? Just see. So when you will move this coil, so I am passing current through this coil, and when I will move this coil, current will flow because the coil, if the coil will come towards this coil, then flux will change, so current will flow and bulb will glow. And if I'll move the another coil, if I move the another coil, then also current will flow. If you'll see, if I move that coil, then also current will flow. Yeah. So to for current to flow, the important condition is to change magnetic flux. So if magnetic flux will change, then only current will flow. So if you move both the coils towards each other, then current will flow. If you move both the coils away from each other, then also current will flow. If you keep any one of them stationary and move another, then also current will flow. So for current to flow, flux should change. So we have two laws of electromagnetic induction. So first is whenever there is change in magnetic flux linked with a circuit, an EMF and hence a current is induced in the circuit. However, it lasts only so long as the magnetic flux is changing. So current will only flow if the flux will change. If the flux stops changing, then current will also stop to flow. Okay, so first law will tell you that what is the meaning of electromagnetic induction. Second law, so in first law we have discussed how that current will flow. Second law will tell how much current will flow. So second law is the magnitude of induced EMF is directly proportional to the rate of change of flux. So the mathematical form is something like this. So magnetic flux is given by N B A cos theta. So this is magnetic flux. N is number of turns, B is magnetic field, A is area vector or area of the coil, theta is the angle between magnetic field and area vector. So suppose we have a circular coil like this. So area vector will be given by value of area, that is pi r square, and direction of area vector, that is j cap. Okay, so this is how we calculate magnetic flux. So magnetic flux can change by following ways. If we can change N, if we can change B, if we can change A, if we can change theta. So if someone asks you how many ways are there to change magnetic flux, so there are four ways: N, B, A and theta. So EMF induced can be found out using two ways. So value of average EMF will be negative of change in flux upon time taken, that is final flux minus initial flux upon final time minus initial time, and instantaneous flux will be minus d phi by dt. So for average flux, you will have two time intervals, but for instantaneous EMF, you will have only one time interval. So if you want to calculate average EMF, then you will have two time interval, but if you want to calculate instantaneous EMF, then you will only have one time interval, like as you can see in the given numerical. Suppose magnetic flux through a coil is given by T square plus 2T. So if we'll see, the value of flux depends on time. So flux is changing. So if flux is changing, then EMF induced will be there. So find EMF between 1 and 3 seconds. So initial time is 1 second. So initial flux will be 3 Weber. Putting value of time here. Final time is 3 seconds. Final flux will be 15 Weber. Putting value of time here. So average EMF will be minus of final flux minus initial flux upon final time minus initial time. So it comes out to be minus 6 volt. And if suppose someone asks you what will be the EMF induced at time 2 second. So only one time is given. So at time equal to 2 seconds, since E is equal to minus d phi by dt. So differentiating the above formula. So t square differentiation 2 and differentiation 2t will be 2. So it will be minus 2t plus 2, putting value of t to be 2 seconds. So it comes out to be minus 6 volt. So this is how you have to calculate average EMF and induced EMF in a circuit. Okay, so Faraday's law, very important. Law number 2, very important, and also how to calculate average EMF and instantaneous EMF. Okay.